Okay, so today we're going to look at composition of reflections. And the first one we're going to look at is if I do a composition of two reflections across two parallel lines. So we're going to fill in these notes in a second, but first let's look at an example together. So I have parallel lines L and M, and I'm going to first reflect triangle ABC over line L. So I'm going to start with this very first reflection. When I reflect ABC over line L, I'm going to count to the line and then go that same distance across. So B to the line is 1, then over 1, and I get B prime. I'll do the same thing with C to find C prime, and I'll do the same thing with A to find A prime. And so now I'm going to connect the points. And now we've moved the pre-image ABC to A prime, B prime, C prime by doing the first reflection, which is the reflect over line L. So we went from pre-image to image. Now we're going to do a second reflection. We're going to reflect this one that's already been reflected. Now I'm going to reflect it over line M. So I'm going to do this next reflection. Here I'm going to go from A prime over, and this is where A double prime should go. I'll do the same thing with C prime. Go over, and this is where C double prime should go. And the same thing with B. This is where B double prime should go. And so now I've done the second reflection. And this green one came from a reflection. We reflect over line M. So now I've gone from B, ABC to A prime, B prime, C prime, to A double prime, B double prime, C double prime. Now, doing this composition of reflections where I do one and then I do another is really the same as doing just one single transformation. This is the same as just doing a translation over. I could go from ABC over to A double prime, B double prime, C double prime by just translating, which we know is like a shift, right? I could just translate right and I would land on this green triangle. Now, when we do a translation, we have to say how much we translate by. And I could find that number by counting over from B to B double prime. If I count the units, I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we went 10 units right. And that is actually a rule that we're going to learn. So in order to find this, and we call it the translation vector, in order to find the length of the translation vector, all we need to know is the distance between the two parallel lines. We don't even have to do the transformations. So I look at this distance here, and for us in this example, my two parallel lines are 5 units apart. You take this number and double it, and that's how you can find the translation vector's length. So if I want to double reflect over parallel lines L and M, it would be the same as just saying translate 10 units right. So now let's fill in these notes. So the translation vector, the composition of two reflections across two parallel lines is equivalent to a translation. The translation vector is blank to the lines of reflection. Now, this is something that we didn't quite look at, but I will tell you that the translation vector, so how much you move in this direction, will always be perpendicular to your lines of reflection. So the answer here is perpendicular. And now the length of the translation vector is double the distance between the two lines of reflection. So those two parallel lines, right? So just like we saw, 5, when I double it, I get 10, and 10 is the length of the translation vector. All right, so this is for parallel lines, and we said that parallel lines, when I reflect over 2, it's the same as a translation. And now we're going to look at another type. So now we're going to do, here's a question first. Quadrilateral JKLM was reflected across 2 parallel lines that are 7 centimeters apart. What is the distance between J and J double prime? Remember, we double the distance between the 2 lines. So if my 2 lines are 7 centimeters apart, then the distance between the points, which would really be the translation vector distance, as it goes from the pre-image all the way to that double reflected image, and that would be 14 centimeters because we just double 7. All right, so number 3, the next one is a composition of 2 reflections across 2 intersecting lines this time. So let's look at an example of this one. Here I have 2 intersecting lines, and for these 2, I made them at a right angle because a lot of times we deal with things that are on the coordinate plane and the X and Y axis meet at a right angle. You don't have to do this over 2 lines that intersect at a right angle. They could intersect at any angle. But we'll do it like this for now. So we're going to reflect over both of these lines. I'll start by reflecting over this vertical line. So when I start with this one, again, I'm going to reflect over. I'll find where each point goes. So here's E prime. Here's F prime. And then I would count and find D prime. And when I connect these, there's our first reflection. And let's label this line L. So that way we can say that this is the reflect over line L, which really could be the y-axis. All right, now we're going to reflect over the line that intersects it. So this line right here, maybe we'll call this line M. And so when I reflect down over M, this one I made kind of big, so I'm going to reflect down. There's F double prime. Same thing with D. There's D double prime. And now I'll do E. Down a little too far. There we go. E double prime. And I'm going to connect the points. And this one is the reflection over line L. Sorry. Mixing things up today. So when I reflect over 2 intersecting lines, I end up down here. And if you compare the pre-image to the very final image, notice how it has twisted, right? E, which was the point up top, is now the point on the bottom. And F was on the right, and now it's on the left. D also moved over as well. And so I could reflect over 2 intersecting lines, or this is the same as doing one single rotation. So I could also rotate to get from DEF to D double prime, E double prime, F double prime. Now remember, for rotation we said we need 2 things. the center of rotation and the angle of rotation. Center of rotation for rotating around two intersecting lines is always going to be at the point that they intersect. So this will be the center of rotation. And then to find how much we rotate by, we look at the degree of the degree where the angles meet. These angles meet at a 90-degree angle. So to find the total angle of reflection, we take the angle they meet at and we double it. And that tells me that this is the same as doing one rotation around this point 180 degrees. All right, so let's fill that into the notes then. So the composition of two reflections across two intersecting lines is equivalent to a rotation. The blank, the center of rotation, is the intersection of the lines of reflection. So we said we were reflecting over L and M, and so where they intersect each other, that becomes our center of rotation, just like we had said. Then it says the angle of rotation is double. So again, it's double. Just like in example 1, where the vector was double the distance, our angle is double the angle formed by the lines of reflection. So in this problem, it says what single isometry would be equivalent to reflecting triangle EFD over line M, then line K. All right, well, notice we have these two lines that meet at a 62-degree angle. So I know that the equivalent, because they are intersecting lines, would be equivalent to a rotation. So it's going to be a rotation about, which says around point what? What point do you think we're going to rotate around? Remember, the center of rotation is the intersection of the lines of reflection. So we're rotating around this intersection at point B. So we're going to do a rotation about point B. And it's going to be a rotation of, well, we take the angle we have and we double it. 62 doubled is 124. So it's 124 degrees. Now this one says to rotate or to do reflecting over line M, then line K. So if I'm moving in this direction, that direction is going to be clockwise. All right, now the last one that we're going to learn about is a glide reflection. The glide reflection is the composition of a reflection, right? It says reflection in it, and a translation. So if you think of the word glide, right, think about somebody that's gliding, they're moving along very smoothly. So glide is just talking about a translation, a shift. So we're going to do glide reflection. So when we do a glide reflection, we start with, I'm going to start with triangle DHS, and I want to reflect and translate so that it winds up being D double prime, H double prime, S double prime. So the first thing that I might do is reflect DHS over the x-axis here. So I'm going to start by reflecting up. D will go right here, we did D prime, H reflects up here, and S goes 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, S prime. And so there's that first one, it's our reflection, and we get the D prime, H prime, S prime. And so there's the reflect part of our glide reflection. And now we're going to do the glide, the translation. And so this one I'm going to have to glide. Let's see, how many do I have to glide it so it lands on S double prime? I just count 1, 2, 3, 4, 5, 6, 7, 8. And if I move all the points over 8, 1, 2, 3, 4, 5, 6, 7, 8. Same thing with D. They should all land on D double prime, S double prime, H double prime. And so we have a reflect and then a translate. And together they make up a glide reflection. So when we look at these glide reflection problems, you might see one similar to how I had it drawn. So I have triangle RTS, and the vertices of the triangle are given here. And then the vertices of R prime, S prime, T prime are given right here. What type of reflection and translation would make up this glide reflection? So you're going to have to actually describe the transformations. So when I describe these transformations, I know that a glide reflection is made up by a reflection and a translation. So the first thing I might do for this one is want to reflect it so that it is up here so that I can shift it over. So if I'm going to reflect up, I want to reflect over this line right here, which is the x-axis. So I'm going to say it is a reflection over the x-axis. And I'm going to draw that right now. So T prime stays where it is, and S prime would go here. And I'll do double since those ones are prime. And R double prime would go here. And there's the reflection. And now we need to do the glide part, right? The translation. How much do I translate this triangle to get it to land on top of this one? Well, I need S to land on S. So I'm going to go over 1, 2, 3, 4, 5 to get S to land on S. And it should be the same for all of the points, R and T as well. So then after I reflect, I need to translate. And we said 1, 2, 3, 4, 5 units. And we moved in the right direction. So we say right. And that's how we perfectly describe transformations. So we have to say what line of reflection, we need to say how many units and in what direction, and there is the glide reflection. All right, on this last page of the notes, it says determine whether each statement is sometimes, always, or never true. Number 6 says the composition of 2 reflections is equivalent to a rotation. Well, this is only sometimes true. When is it true? The composition of 2 reflections is equal to a rotation only if they're intersecting lines, right? If they're parallel lines, it's a translation. So that's why it's not always true, right? Because I could have 2 parallel lines. But it is sometimes true if I have intersecting lines. So for this one, it is sometimes true. And I'm going to say in parentheses, intersecting lines. All right, and isometry changes the size of a figure. This is never true. In all of the transformations we've done, we have not changed any sizes. We have only changed location. So that's never true. The next one, the composition of 2 translations is a translation. This is always true. If you move up, down, left, right, doesn't matter how many times you do it, you're still moving and shifting the same image all around. And so that is always still the same as just a translation. And last says the composition of 3 reflections across parallel lines is equivalent to a single reflection. Let's see if this is true. And I'm going to pull back up my parallel lines example right here. Let's say I draw one more parallel line. I'll do it right here. So line, let's say line P is also parallel to L and M. Now, if I reflect A double prime, B double prime, C double prime over this line, I'm going to get B triple prime, C triple prime, and then A triple prime. I'll connect the points. And now I've reflected over this line to get this transformation. Is this going 1, 2, 3 times the same as if I just reflected once? And the answer is yes, that's always true, right? Look at just these two. If I do one reflection, notice how these are symmetrical on both sides. Let me cover up the middle. Can I get from A, B, C to A triple prime, B triple prime, C triple prime with just doing one reflection? Yeah, I sure could. If I put my line of reflection somewhere in the middle here and I reflected over the ruler, I would get from here to here by doing just one single reflection. So the answer for this one is always. This one is also always true.